welcome. Almost the end of the conference. I hope you all had a great week. Thanks for joining. Hopefully this should be fun. The idea is to talk about something I did a couple of years back, actually, beginning of the pandemic, but it's been a long journey, and I want to share a bit about this journey, how I basically ended up building some kind of artificial nose using really low-cost, low-tech kind of technology, initially starting with Arduino, and that was a great experience, and then I ended up eventually migrating to Zephyr, and that was even better. For those who don't know me, I'm Benjamin. I'm a developer advocate for the Zephyr project, and I'm French, so I do like baking, among other things. I do like yummy food, and I've been trying to perfect my bread recipe for the probably past 30 years, actually, and I'm still not incredibly happy about how the bread turns out. It's never crispy enough. It's never like risen enough. It's hard. I mean, some of you might be recognizing what I'm telling here. So back in, I remember, like 2019 or 2020, when it was the first few months of the pandemic, everyone stuck at home. I was like, okay, this might be a good opportunity, just like pretty much billions of people in the world. This might be a great opportunity to bake even more bread and try to improve my recipe. And I was like, hey, this is maybe finally an excuse for me to do some machine learning. I'm just like probably pretty much everyone in the room. I'm supposed to be a software engineer by training, except that I'm really bad at all things math. And whenever I would open a book where it's like, oh yeah, neural networks, it's easy. Look at those handwritten digits. We're going to do like matrix, like feature extraction, layers, whatever. It was just, I couldn't really understand how to make anything useful out of what the book was trying to tell me. Except that, well, at that time, and now you're hearing that more and more, and Jordan was talking about it yesterday, and there's this notion of TinyML, which, by the way, that's not the name of a product. It's just the name of an approach, which is taking all things machine learning and neural networks and whatnot, and making it fit and run on small devices, with like the main idea being, I mean, you want it to be efficient when it comes to processing power, but maybe even more importantly in terms of energy. Like you want to build devices that are battery powered and that are smarter. And I was like, okay, it looks like this would be the kind of thing that I would run on those kind of Arduino devices that I'm very familiar with, and maybe this will be a way to, rather than looking at bitmaps and like pixels in something like quite abstract, like the handwritten digits, maybe this will be a way for me to look at more like tangible things, quantities, and correlate things like my intuition was telling me, things like, okay, I have a sourdough starter, I'm sort of like eyeballing it, I'm smelling it to figure out whether it looks like it's ripe and perfectly fermented or not. Maybe the machine would be able to do the same, right? And I would basically smell using gas sensors, smell the sourdough starter, bake the bread, figure out whether the bread is like a 1 out of 10, 8 out of 10 kind of bread, and then rinse and repeat and have some kind of like training material. And like maybe that was finally my way to dive into TinyML. And thanks to, again, Arduino and like the super awesome ecosystem of libraries for like sensor drivers and like graphical user interfaces and whatnot, and other tools out there. Some of you might be familiar with Edge Impulse. It's, by the way, a plug of their solution, but it's basically tooling on top of TensorFlow Lite and like a really nice, basically web interface where you start feeding your data, and it's like very visual, and you start labeling your data sets. You still know nothing about the math behind it, but at least you're able to train a model and do something useful in the form of just spitting out an Arduino library that you can easily reuse. And I ended up building, in literally a couple hours, minus the fancy enclosure that came later, but in literally hours, just like, I mean, the Arduino way, frankly, I put some pieces together and I was able to smell a few things. So didn't start with bread actually, because it would have taken, I guess, many, many hours or days to get enough training. I rather basically took what I had in my shelves, spirit and coffee and whatnot, smelled using a gas sensor, and we will talk about it a little more in a while, smelled and captured some data and used that for basically training a model that could then recognize things. So that was fun, and that was like, I'm by no means sort of like trying to brag when saying it took me only a couple hours. It's actually quite the opposite. Like I really felt that I had, well, finally learned a few things about TinyML, but surely many people before me would have done the same. Like it was a crappy, quite frankly, sensor, a very simple model, and sure I was smelling things, but yeah, that's what ML does. But people were like, when I started to talk about it on Twitter and social media and whatnot, people were like really impressed. Maybe I guess the funny enclosure helped a bit. I think I have it in my bag actually. Do I? Yeah, whatever. Funny. So I also learned Blender in the process. That was also a nice excuse. But yeah, people were all about it. It ended up making the cover of Make magazine. That kind of really didn't help my imposter syndrome there, because I really felt like it was something, if not trivial, at least nothing special. But yeah, I mean, it inspired people. And I think there's a lesson there in terms of, even before thinking TinyML, we're all like more or less embedded developers, IoT developers, however you want to call it. What I've realized, and I'm pretty sure it's still the case today, many people, including experts of the domain, like chemists and people from the food industry, etc., which I thought would know that it's possible to smell things or to measure gas concentrations using sensors, they didn't even know that. So let alone hooking up TinyML into that. People, when they think sensors, I think they think like temperature, humidity, the kind of thing that maybe they experience in their households, but there's many, many more physical things that can be measured and potentially fed into AI algorithm that I think the sort of the industry at large doesn't necessarily know about. So that's one. And yeah, it inspired people. So that was pretty cool. So it ended up being published in Make magazine. There was this, actually I only realized a few minutes ago, this sweater that I'm wearing from Pasadena University. Yeah, there's this kid out of Los Angeles. He found the magazine. He was really sick when he was, I think, 8 years old, pretty much almost died. And turns out that doctors could never diagnose the fact that he had fungal pneumonia, because, like, I mean, it's kind of a hard disease to diagnose. Only through like X-rays, maybe you can spot it. But now that he grew up, there's been some like scientific research around the topic. It turns out that apparently you can smell the markers of the disease in someone's breath, like some. Essentially, if you smell like lemon, and I don't know what was the other kind of like essential marker, that could be a good sign. So he did something like pretty amazing with like an artificial respirator, etc., to train the data. He did that, except that he's 13 years old, is like obviously brilliant, but he's no programmer, and the only code he had access to was my crappy Saturday afternoon Arduino 2,000 lines of code super loop. And so I felt kind of like really bad. And we will talk about more about why that eventually sort of led me to convert to Zephyr and try and do something more, slightly more future-proof, let's say. Quick side note on, because again, I said that there's this whole thing of people not necessarily being super familiar with all the ways we can sense the world around us. In case you're interested, and I'm no chemist or electrochemist, but basically the gas sensor that I'm using for the project is effectively a 4-in-1, like those 4 pieces of MOS, effectively, that you see on the PCB. They all react to, one reacts to volatile organic compounds, the other to alcohol, carbon monoxide, and nitrogen dioxide. And the way it works is that there's they're being heated up, and due to the actually heated up really warm, which means also that you have lots of power. It draws a lot of current, but when it gets really hot, it starts reacting with the chemical compounds in the air, and there's some kind of redox reaction happening, and so you can measure basically a change in resistance, which that of course MCUs are pretty good at. And so say you have 10 parts per million of VOCs, maybe your sensor will register at 100 ohms, and you have 10 times more, the resistance will be twice as big, whatever. This is where, I knew that I wanted to sense and smell data, and my intuition really, and this is where also, by the way, the tools like Edge Impulse, and I'm sure there's many others, this is where I was able to sort of finally bridge this gap I was having when reading the books. They were like, oh yeah, a handwritten digit, it's easy, it's 20 by 20 pixel, and you have matrices. Yeah, no, I don't care about matrices. I'd rather sort of see and feel the data. And so if I were to smell, say, whiskey here, I could look at the data and be like, oh yeah, okay, I know. If I were to write this as actual code, I would probably figure out something like, if nitrogen dioxide is going up in a steady way, if carbon monoxide is kind of flat but kind of fluctuating as well, this is whiskey. And so this, among other things, allowed me to finally, I guess, understand things like feature extraction. In this case, it's really basic statistics, looking at things like, on a given time window, what's the minimum, the maximum, the standard deviation, the average of each and every quantity, because those are going to be the sort of the bare minimum kind of inputs that I want to feed into my algorithm, which effectively is I need to solve an equation where if I feed you with the average level of VOCs, the maximum level of VOCs, etc., and I tell you that this is effectively ambient air or whiskey, please remember that so that later on, training a model basically. So yeah, and the model, by the way, is really like that. There's no convolution or no there's not much. And you could do basic clustering probably at the end of the day, but yeah, that's it. And so that was pretty fun to build. Arduino, again, I told you it was really fun, or was it? Because there's actually a lot of things that's going on in there. Just if you've been playing with Arduinos, I think, again, you know what I'm talking about. You keep adding and adding stuff, and it does a lot of things. There's a hardware interaction with the sensors, obviously. There is a fan that can draw some the smells into the contraption. Graphical user interface, ideally, you make it battery powered, connecting to the Wi-Fi. We're going to talk about some of the potentially IoT use cases behind things like an artificial nose. But if you start building that in a la Arduino, then you might be in trouble, because you've been training a model where you have training data, which is effectively, in my case, only sampling gas sensor data at 10 hertz for a couple seconds. That's actually enough to capture the minimum, average, maximum, etc. I was referring to earlier, which effectively represents the fingerprint, if you will, of a smell. But the fact that the data is acquired at exactly 10 hertz, that's actually quite important. Otherwise, you get your model giving you completely bogus outputs. So in the loop, one thing that I do is acquiring the sensor data. That's pretty fast, and I can do that. I can feed it to TensorFlow Lite for microcontrollers to actually run my inference. For what it's worth, that's also really fast. It only takes really a couple milliseconds on the 200 megahertz Atmel Cortex M4, I think, chip, M4F. So that's still fast. Then there might be some kind of UI interactions. There's a UI that I need to refresh, which, again, hopefully, takes, I don't know, tens of milliseconds. But then I might actually want to send data to a server, and that might take a long time, and then my loop is all effed up, and I'm not able to sample the data at 10 Hertz anymore, which, I mean, yeah, there's probably ways to still do that in a kind of super loop and like have some kind of basic scheduler and still stick to the Arduino way. But what I realized is that, I mean, I'd rather migrate my code to Zephyr. Actually, I should have removed the slide that introduces Zephyr. I don't think it requires an introduction, but yeah, I want to sort of walk you through some of the things, some of the concepts, subsystems in Zephyr that actually proved quite useful, because that makes the code and the application in general so much fun actually to work with. Things like sensor data acquisition, like it's something that can now happen in a completely dedicated thread, and I can make sure that, yes, it's going to run at exactly 10 Hertz. I can have also an abstraction of the underlying actual sensor that I'm using. The only thing my model cares about is reading gas concentrations. It doesn't really matter whether it's a Bosch sensor or whether it's the sensor from Seed Studio that I've been using initially. So that's pretty nice. It also makes it, like the sensor subsystem, makes it quite easy to simulate the data, emulate or simulate, however you want to call it, which can be useful. There's power management integrated in it, like Jordan, again, I guess, mentioned, among others, today. This one has a small caveat, which is that the technology for the gas sensors requires, like I mentioned, for the sensor to be really, really warm. So not only does it draw a lot of current, but you're kind of stuck with it because it takes a long time to stabilize. So it's not like you can go to sleep, turn off the sensor, and then turn it on and get a reading in the next second or so. You need to wait minutes, usually, for the readings to stabilize. So in theory, you could hook up power management, but it can be tricky. And then feeding the data to TensorFlow Lite. So a couple of things to say there. One is TensorFlow Lite for micros is like already available in Zephyr as a module. So like pooling it in your system, getting automatically CMCs, DSP, and CMCs, and then potentially to kick in, that's there. So you have like great acceleration, etc. And in my case, one thing that also was quite interesting was that I'm by no means a great embedded developer, but I'd like to think that I know how to write apps in general. And so I want to write my artificial nodes just like I would be writing like a regular, I don't know, web application or something like at a really high level, right? I don't really care about the really low level stuff. So in my head, like I want to be able to do something like sensor task, sensor thread does its stuff and makes the data available to the rest of the system. Similarly, the inference thread, which should hopefully run with a much lower priority and like be when it can, does the same. Subscribes to any hypothetical sensor readings and then posts, publishes, whatever, the results. And then there's a GUI that subscribes maybe to both. That needs to visualize and display sensor data as well as the inference results. And so I've been basically building on top of ZBus for doing just that. And so then there's the GUI that comes into play. It was really, really ugly in the past with the Arduino version, using basically manipulating pixels almost directly with some kind of abstraction. But I mean, it's really fun initially, but then when you want to look, when you want to make something look pretty and don't like have, not eat up lots of memory, etc., then it's not fun anymore. So there is a really good integration in Zephyr for the LVGL graphical toolkit, graphical framework. We have a really like super passionate and productive maintainer there who really keeps track of the upstream LVGL project. So you have basically the same LVGL as everyone else, which basically allows you, again, to my point of myself being more an app developer, I write a GUI using like widgets and like callbacks on my buttons, etc., my buttons, they can actually be buttons as per the Zephyr input subsystem, or the touch screen is effectively like, as long as I have a touch screen driver and I've hooked it up properly in my device tree, then I can start using it in my GUI. And when I start like dragging sliders around, etc., it will just work. Memory management, similarly, you can like leverage the memory attributes and whatnot to really fine-tune the way memory is going to be managed. And one thing that's also really, really cool, it's not necessarily like LVGL specific, frankly. It's more about the native simulator infrastructure that we have in Zephyr. On top of your like Linux box, your Linux desktop machine, you can actually run your app, potentially with simulated sensors, like I mentioned before, and simulated display as well. Like the screenshot you have here is the same app that's running on my actual device here, except that it's on my desktop. So like the sort of the round trip time for prototyping, troubleshooting is way faster that way. And putting all the pieces together, ML inference, ZBus, display, like LVGL display, literally the code, like again, the app code looks a bit like this. Like I have, I'm using like the ZBus macro that allows me to listen to particular messages, and as soon as such a message is being posted, then I get it and do whatever I want with it, which in my case would be calling whatever LVGL API allows me to create a fancy GUI, displaying a label, feeding data into a chart, you name it. And so we can actually probably see that in action now. Running the demo on an M5 stack ESP32 device. So obviously, I mean, you know that, but it's good to say it out loud. The app is very portable. So I have this guy that I mentioned before, like originally the Weir terminal that I used, it's a SAMD51 Cortex M4F, same app, nothing needs to be changed. And yeah, we have a chart. You might not see it all that well, but all the horizontal lines, those are like the 4 channels, the 4 gas sensors, and it says that it's reading ambient noise, ambient air, not ambient noise, right now. And the sensor is right here, and I have a smelly thing right here. Let's figure out what it is. Should work, except I might not have enough hands to do it properly, but there we go, ambient. There we go. Lemon, it says that it's lemon. We see the, so yeah, there we go. It's really kicking in. So you can also tell that the sensor is not that sensitive, not that reactive. That's just the technology. It's like $20 worth of sensors. And by the way, I think like the Bosch sensor I mentioned before, it's more like around $4. So there's, I mean, different technology, but yeah, it says that it's lemon, and the gauge is saying the sort of the confidence level. So it's sort of oscillating. Yeah, I guess now it's 80% sure it's ambient. I mean, you get the idea. I haven't retrained the model recently, so it might be that the sensor is full of finger grease. It might be that the conditions here are slightly different, but the model that I used is really literally just minutes worth of data, so obviously it can probably be fine-tuned. One thing that's also part of, and was part of the initial proof of concept, I guess you could say, is trying to demonstrate that beyond the fun or silly aspect of this whole project, there's also this idea of, hey, it might actually be a very valid use case for IoT in the form of, what if I were to stick this kind of device in the restrooms of a facility, office buildings, to figure out when the air starts smelling not so nice, to send people and clean, right? And you don't want to send someone twice a day or like twice a week, whatever, to a place that doesn't necessarily require that much cleaning, right? I mean, offices, maybe people use them less post-COVID, and so having a device that you stick, like a wireless device, you stick in the ceiling of the restrooms, and posts data to an IoT server, that might actually be a very valid use case. And yeah, we can talk about, it can go both ways actually, posting data, but potentially also pushing updates to the model, why not? So yeah, I mean, obviously Zephyr has a great network connectivity stack. Part of the migration process for me, and everything's on GitHub by the way, was to use MQTT to post data, like whenever there was a new inference result that's different from the previous one, then you publish to a server, and that's something that could be used again for this kind of use case that I was mentioning. And then you start tapping into things like the whole digital twins buzzword, which in fact might actually be more than just a buzzword. If you think about a company that's sort of specialized in cleaning buildings and like doing maintenance work, etc., they probably already have like a really rich information system where they manage like all their facilities, they manage the schedules of their employees, you name it, like the billing, the invoicing of the customers. So you have this like existing database, but what if you start like augmenting it, like hopefully you code that, right? Like you have devices maybe that are part of also of this same sort of knowledge graph, if you will. So let's say we have an artificial nose device, and as part of the provisioning process, whoever's going to install the device in the third floor of Tribune Tower in Chicago, they will effectively make this association, which allows, like, it's basic database stuff, if you will, but it's still worth, again, saying it out loud, I think. As soon as such a device starts sending information, like very raw information, just like it smells, then you can do whatever in your system, right? And like query the system to be like, oh, who is responsible for cleaning floor 3 of this particular building today? Oh, it's John. Oh, but it's on holiday today, so it's actually Jane that we need to text or send an email to like send them on site. So that's one of the things that this whole project, I guess, or like a use case enables. And then there's more, of course, that I was happy to be able to use as part of the migration process, things that I didn't have when using the Arduino way, all the configurability. Like if I run the device on the application on a device that has a small screen, like it's really, really easy to make my GUI code adapt accordingly. Like maybe I want to show a graph. If I'm running on a super tiny display, I will only show the smell kind of thing. And that's something that you can do like just out of the box. You have kconfigs that expose and give you access to the screen resolution, whether you have network connectivity and whatnot. Some of you know that, of course. Testing framework, like it's actually quite nice to be able to do, especially in this context where I'm starting and thinking about decoupling really all my tasks and processes. I'm doing sensing on one hand, ML inferencing on the other, and then also the GUI. Like this is really independent. ZBus in the middle. Testing that is actually way simpler, and especially with things like Twister, etc. Taps also into the whole CI story. Like anytime I, of course, do a push on the project, I can check against all the devices and the boards that I'm targeting. So that's pretty cool. And what I find even cooler, although I didn't get a chance just yet, is Zephyr keeps adding stuff that's very relevant to this project and to hopefully many more. But you've heard about, so I was saying LLXed until today, but I'll start saying Lext. Dynamic extensions. The model, the AI model that runs the application today, as of today, it smells good air and nasty air. It turns out that maybe in a couple of years, and apparently like that's what some scientific research seems to say, there might be ways to smell COVID in the air. So maybe I will be able, with the same hardware, to have a better model that's able to spot that using Lext. I could theoretically, over the internet, push it over the wire or over the air to update the model on the fly. I could add geolocation to the mix. I could add more types of displays, et cetera, et cetera. So that's pretty cool. Everything, like I said, is open source on GitHub, including the 3D enclosure, should you want to print it. Originally, I thought it was a bad design, but apparently many people around the world have been printing it, so I guess it works. The actual Zephyr-based project is this particular URL. The other one would have been the legacy project if you want to get the parts. I'm not getting anything out of that. I guess I should, because I think they've been selling quite a few, but among others, see it as like a SKU, like one click on their website, you will get the Wio terminal, the gas sensor, the baguette. No, I don't think the baguette comes with it. And yeah, that's it. I think that's what I had, frankly. We have time for questions, so I hope you have some. There's one here.
Great talk. I really liked it. So did you manage to apply your digital nose to improve your baking?
I should have a slide about that, because that's actually the first question that everyone asks. I moved on. Like I figured I had a lot of fun with the whole thing, but the thing is, and well, I actually kind of used to have a slide about that. The thing is, back in May of, again, I think it's 2020, right? Whatever, really early in the pandemic, there wasn't even flour on the shelves in the store. So I would have needed to bake dozens and dozens of baguettes, right, to train the model and eat the bread, which might have been also a problem too. But so yeah, it was way much easier to literally spend minutes smelling whiskey and coffee and whatever I had. And for what it's worth, like with a very simple model, very crappy sensor, my initial tests, like as part of this first Saturday afternoon, was with booze, like I think I mentioned. And yeah, like different kinds of whiskeys, it would be able to pick up the difference, like a really peated whiskey versus a slightly less peated one, versus vodka and rum and yet another rum, I think, like those 5 spirits, including like 2 rum, two whiskey, it worked. So that's, but yeah, no bread, never actually tried.
So now you are an alcoholic instead.
I also have one more question.
No, like the thing is that I didn't need to drink, as opposed to the bread. I might have become a celiac or whatever.
I was also wondering what your data collection process was to build up a data set to train your model.
Yeah, so and so that's actually a feature that's still in there, also that I ported from the Arduino legacy app. So there's this edge impulse thing, but it will be applicable to other sort of workflows that makes it really easy to, so the way it works is that I build the app with sort of a flag on which, when it's on, the device would dump sensor data to the UART in a CSV-like format. And then the edge impulse thingy has a daemon that runs on your machine that forwards the data to the cloud. But again, it doesn't have to rely on the cloud. And it makes it really, really easy to feed data in somewhere, label it. And so you can be like, okay, I want to capture 2 minutes worth of data. So it starts listening to this stream of sensor data. Then you label it, you visualize it. I think I can probably pull it up just like real quick right here. You can visualize it. It suggests you some basic DSP slash signal, slash statistics blocks that you might want to use to do the initial feature extraction. And then you're good to go. Like it's, so let's see. So that's training data. So exactly like I said, like I click, I'm like, okay, I want to capture 30 seconds worth of data that I know. Oh, I'm not sharing, sorry. Should have told me. All right, I'm not duplicating the screen, so it might be a challenge. Yeah, whatever, yeah, that's enough. So those are all the captured samples. So 30 seconds of whiskey on May the 7th of 2021, blah, 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 blah. And then the tool automatically suggests some feature extraction things that would work well for time series data. So would you like to try to average the data on a two seconds window? Would you like to try to blah, blah, blah? And then once you have that, it does kind of the same process for suggesting some very basic, like fully connected neural networks, and then you're good to go. And then, like I said, once you're done with it, you realize that maybe there's just really little actual, very few features that actually contribute to the results, so few that maybe you could actually do the whole thing with just like an if. Like if VOC is above this threshold, it's always coffee sort of thing. But it also works with the neural network. And if you do all the optimizations, it's not necessarily going to be more costly in terms of RAM processing power, etc. So that was my long answer, I guess.
Hello. What will be the difference between this artificial nose and then air quality sensor? Because I know those are also using gas sensors.
Yeah.
Or
so
maybe you can use them at a large scale, like for air sensors.
From what I know about air quality sensors, there's an aspect to them which is they look also at particulate matter concentration. But one thing that I often tend to mention with, I mean, I call it an artificial nose. It's by no means like anywhere close to a human or a dog nose. But it's a device that smells, but in fact, it could use whatever kind of sensors. Potentially, just like we do sensor fusion with accelerometers and gyros, etc., we could think of doing the same. I mean, what I'm trying to say is, if you want to build a device that makes up the difference between orange juice, water, and wine, if you can afford or if you have access to a color sensor, maybe you can feed that also in the system, right? And then you have concentration of VOC, air quality, humidity, color. You feed all of that into your like training workflow, and then as part of the training, you will realize that, well, you know what? Only the color input is required, right? So yeah. Anthropomorphism is something that we tend to do maybe too much of for those kind of applications, I think. And yeah, it's not because it's a nose that it has to use gas sensors, I guess is what I'm saying.
Any other questions? No, I have a question. So what's the next step? Test sensor?
What's
the next step after the smell? Taste? What about taste? Do you have any idea? Did you think about something else to take it beyond just smelling?
Beyond just smelling, no. I would love, so a couple of things. I would love for that to help. And I was having discussions with folks around accessibility. There's lots and lots of people who suffer from anosmia. So who lost the sense of smell during COVID, or for like they've had a really bad cold and they lost their sense of smell forever. So putting the device in a fridge to figure out when the food gets spoiled. Like I actually had someone somewhere where I was sort of demonstrating this device came to me and was like, last week I kind of almost died because I ate, like I don't have the sense of smell. I ate some ham or eggs or whatever. I wasn't sure, but I ate them anyway, and then I was really, really sick. So there's that as part of the what's next. Like it would be great for someone to pick it up. It might require better sensors. It might require the sensor fusion thing that I was referring to. Maybe that could help that. And also, what I would like to see is, just like we have all those data sets for training like facial recognition algorithms and like image, video recognitions, all those labeled data sets for images. I don't think we have, I know we don't have the same for smells. And so at some point, ideally in open source, it would be great to have that. Like it comes with tons of challenges regarding how do you even represent a smell in the first place. But yeah.
Okay. Thank you, Benjamin. And
thanks.
Yeah, see you around.